Hello, my name is Don Metzger. This video describes the OFDM multipath tolerance and does it using a demo on the Analog Devices AD9361 chip. There are many excellent resources on YouTube that describe how OFDM as a signal type is resistant to multipath, but I didn't find many good resources that actually show it in action. That's what this video does. The emphasis is not on theory, but on practice. Here's the overview of the video. First, we'll talk about OFDM and how that has become the waveform of choice for so many different consumer standards. Then we'll move to the measurement setup and show you the Analog Devices AD9361 chip that we're using and how we're making these measurements. We'll talk about the waveforms that we'll be using, and then we'll jump into doing some multipath demos. We're going to be comparing some PSK phase shift keying waveforms with the orthogonal frequency domain multiplex waveforms, and then we'll have a conclusion. Here's a list of some of the consumer-oriented standards that are now using OFDM. The earliest one that I could find was 1997 with DVB-T, Wi-Fi or wireless networking for computers. That's now using OFDM. Cell phones, 4G, 5G, are using OFDM. Cable modem, transport with DOCSIS 3.1. And finally, the more recent one, cordless phones, DECT, in 2020. My career predates cell phones and Wi-Fi and digital video broadcast and things like that. So it's interesting for me to see all of these different major consumer standards that have adopted OFDM as their waveform. Here's the measurement setup that we'll be using. The big green board is a Xilinx AMD ZCU102 board, and it's running Analog Devices IIO software. The blue board is an Analog Devices FMCOMS 3 eval board, which is used to eval their AD9361 transceiver chip. I've got it set up with 2 transmit channels. Each of those has a 20 dB attenuator, and then the channel is being modeled through combining those 2 signals together through a splitter combiner. And we have one receive signal that goes back into the transceiver chip. We'll be using software by QIQ Systems. QIQ Generator will make the waveforms for us. QIQ Multi-Transceiver will run the multiple transmit signals. And then QIQ Receiver will do the demods for us. Here are the waveforms that we'll be using. For the OFDM waveform, I'm going to use a 4G LTE cell phone signal. The sample rate is 30.72 megasamples per second. We'll be using the 10 megahertz bandwidth, PUSCH, the uplink shared channel, and it has a normal cyclic prefix. We'll be doing both QPSK and 16QAM symbols on the subcarriers. The occupied bandwidth of this signal is 8.99 megahertz. That's the orange trace in the spectrum on the right. To illustrate the problems of multipath, we'll be running a PSK QAM type of signal, also at 30.72 megasamples per second. We're going to use the symbol rate of 9.216 megasymbols per second with a root raised cosine alpha of 0.2 for the transmit filter. That gives us also an occupied bandwidth of 8.99 megahertz. That's the yellow trace in the spectrum over there on the right. We'll be using both QPSK and 16QAM symbol types. Just as a note, that strange symbol rate, 9.216, is 3/10 of the 30.72 sample rate that we're using. All right, we've booted up our system. It's running, and I've brought up 2 pieces of software. On the left here, these 2 plots, this is QIQ Multi-Transceiver. It's the application that will be interacting with the eval board. And then the data that comes from that will get routed over to Quick Receiver to do a demod on it so we can see signal quality and a bunch of different aspects of the waveforms. I'm going to start with Quick Multi-Transceiver here. First of all, we want to make sure that we are connected to an FM Comms 3 board over the network at this IP address. I've created a couple of different transmit waveforms, several that we'll be using. At first, we want to start with a QPSK waveform. So here's a folder, and I've used Quick Generator and have put these files in here that are waveforms. So I'm going to start with the QPSK at the 30.72 megasamples per second, and I'm going to do that in both of the transmit channels. So the same signal being used for both of the transmit channels. For control of the chip, I'm going to transmit at 1 gigahertz, receive at 1 gigahertz. We're going to capture 60,000 received samples using our one receive channel. We're going to be doing an LTE type of sample rate, 30.72. Transmitter 1 is going to be on, transmitter 2 is going to be on, receiver 1 is going to be on, and receiver 2 is not connected, and so that's turned off. Finally, let's add some transmitter processing. This is software that gets applied to the signal before it goes to the chip to be transmitted. And I'm just going to add minus 60 dB of gain. So I'm going to attenuate one of the channels, the second channel, very significantly. So it's really not a factor at all. I'll hit the start. So we are transmitting the two channels. One of them is very highly attenuated, and then receiving this waveform. Now with our software, we can route data from one application to the next. So this application, multi-transceiver, can do 4 transmit, 4 receive waveforms. There's a lot of windows associated with that. I've only got the one receive channel up in this case. Also, when we do demods, there are lots of windows possible in that scenario. So we separate those two apps, and I'm going to route data from this app over to this app over here. So I'm just going to, I've already set it up, just start it running, and so it's gathering data that's being sent interprocess from this app to this app. So here is that QPSK waveform, a normal PSK type of signal doing a transmit and receive, and the multipath is really not very significant in this case. Okay, the first thing let's do is let's introduce some multipath by taking that second transmit channel and not doing 60 dB of attenuation. Let's try something more like 20 dB of attenuation, and let's give it a time delay of 200 nanoseconds. So all this gets done in software before the signal gets sent to the chip for transmitting. So as soon as we hit that, you'll notice that we start to see something over here in the demod. You start to see that the spectrum gets a little bit of character here. It's not flat anymore. And we see an interesting pattern starting to develop on the final symbols from the demod process. I want to make one adjustment to the multipath signal here because I think it gives a lot of insight into what's really going on. I'm going to go and say that the multipath signal only is 15 dB attenuated with respect to the main signal. And you'll see as soon as I do that, what you can observe, I'll stop the playing here. Notice how our final symbols here have become QPSK with QPSK on top of it. That's what multipath is. Multipath is two copies of the same signal. One copy of the signal is generally attenuated and arrives later in time compared to another one. So basically what you begin to see is QPSK on top of QPSK. It's just a strict superposition. You're just adding two QPSK signals together. And so you begin to see this QPSK on top of QPSK pattern in your final DMOD. This amount of multipath wouldn't be causing symbol errors because it's not enough to push us across a symbol error boundary. But it does degrade the EVM significantly. The EVM of this final signal here is now 18%, which is a significant degradation. You'll notice also in the spectrum here that we're starting to have these dips here, and these dips are at a very specific separation, and that separation is related to the timing of the multipath. So what I'm going to do is I'm going to go in here and start up our processing again, but this time I'm going to use 3 dB down multipath. So very, very strong multipath. Still will keep the 200 nanoseconds of time delay in that multipath signal, but very strong amplitude in there. So let's start that running. Now you can begin to see a very strong pattern on the top of the spectrum. And if we stop this, and you go in there and you look at the frequencies that we're dealing with, remember 1 gigahertz is our center frequency, and this is about 2.5 megahertz to the positive side. This is about 2.5 megahertz to the low side. That's a 5 megahertz separation, and you take 1 over 5 megahertz, and that's 200 nanoseconds. So the 200 nanoseconds of delay that our multipath signal is coming in later than begins to create these interesting character in the what used to be a flat top spectrum here. And you'll notice now that there's a lot of error in here. It's still QPSK, the symbol should be here, but now it's a big QPSK on QPSK with yet another under. Anyway, it gets to be very complex at this point. The DMOD would not be processing any signal of use at this point. The bit errors would be way too large. All right, let's go run our OFDM waveform. So I go up to File and I select Transmitter Files, not for the QPSK waveform, but instead for the LTE waveform that we want to try out in our multipath environment. And I'm just going to begin with no multipath in time, and again our minus 60 dB for that multipath signal. So it's basically suppressed at this point. Let's start the waveform playing. Let's go over here and tell it to do an LTE DMOD. I've already set up the parameters for the DMOD, so we'll just start that running. Okay, so here is our LTE waveform, and I'll stop and make note of some things in here. We've added an additional plot, which is EVM by subcarrier. So as you go across the frequency band of an OFDM signal, across the frequency band and spectrum here, I'll show it to you there. There are numerous subcarriers. In this case, there's 600 subcarriers across that frequency band. And we track and compute the average EVM for those subcarriers and the max EVM, and we compute an average EVM for the whole signal. The joint time frequency plot, where frequency is horizontal and time is vertical and the color is the amplitude of the signal, has an interesting pattern in it. That striped pattern is the reference sequence that is used to align in time and frequency for this particular type of OFDM waveform. Okay, this is the moment we've all been waiting for. Let's introduce some multipath into our signal. So let's start it running here, and let's go into our transmitter processing. Let's introduce some time delay, that 200 nanoseconds, and let's go 20 dB down for a multipath signal. So you'll see again a little bit of character develops across the top of what previously was a flat top spectrum. Now let's start the DMOD operating. And you'll notice the DMOD, the data is the same, it has that character here, but wow, symbols look pretty good. In fact, EVM's very much similar to what it was before we introduced the multipath waveform. Let's go in and introduce some more multipath into this. Let's increase the amplitude of that multipath signal up to -6 dB. Again, you see that characteristic pattern where it's going to be 5 megahertz between these due to the 200 nanoseconds. So it's got the same sort of interference that the regular PSK waveform had, but the DMOD is staying pretty solid. The EVM has increased a little bit. We were having about 3% EVM before. Now we're up at 3.7% EVM, but it's hardly making any difference at all on our signal. For our final test, let's stop these signals playing. Let's bring up a 16 QAM type of waveform, regular PSK QAM type of signal. So here's our 16 QAM. Here is the other one doing exactly the same signal. And let's start that playing. And now I think I'll go 500 nanoseconds of time delay and maybe 10 dB down multipath signal. So now you can see the ripple pattern is even tighter, and that's because we did a longer time, which means a tighter frequency across the spectrum. And let's route this over to our DMOD. We need to go in here and tell it that we are doing a 16 QAM type of waveform. And let's start the DMOD working. And you can see that that's not going to work. Almost totally jammed. There's no useful information that's going to get through in a scenario like that. And for our big finish, let's switch over to an OFDM type of waveform. So I'm going to stop both of these. I'm going to go over here and say for transmitter 1, let's send it our 16 QAM version of LTE. Push. Do that in both of these. I'm not going to make any change at all to the multipath. So same looking pattern on the top of the OFDM signal that we saw for the 16 QAM signal. I'm going to go over here and say we're going to do an LTE DMOD with 16 QAM symbols on the top of those, and start that running, and wow, that's a pretty good DMOD. Given that the 16 QAM type of waveform was totally jammed. This is getting through pretty well. Again, average EVM better than 4%. So that's pretty good. So why does OFDM behave this way? Well, that's a little beyond the scope of this video. There are many excellent theoretical discussions about OFDM and why it behaves better in Multipath. I just thought it might be interesting to see it in action, to see what it really looks like from a signal perspective. So what we've seen are that PSK QAM type of waveforms have difficulty in multipath environments. That superposition, that adding of signals to signals makes the DMOD struggle to be able to recover the waveform. The OFDM waveforms withstand the effects of multipath much better. There was some degradation in EVM, but the DMOD continued. 4G LTE, as an example of OFDM, even allows for an extended cyclic prefix, which increases the multipath tolerance even greater than the example that we ran here. For more information about the software that we used in this demo, you can visit us online at quicksystems.com or send us an email at sales@quicksystems.com. Have a good day.